Okay, continuing our work on assignment 2. We'll start with the ones I haven't done, number 13. Notice the table of contents will be at the end because I don't know what it is until I've made the video, so I can't put it here. So I'll put it at the end of the video. So if you're looking for a specific problem, you can go to the end and you don't have to scroll through the whole video. So we're going to start with 13. So go to Moodle, open 13 up, draw the diagram, label all the charges, and show all the vectors. So pause the video here, do that, and then unpause the video and see what I did. Okay, here's my diagram. Realize that this problem has randomized numbers, so you're probably going to have different numbers than I have, but you can watch the method. So for me, Q1 was 2Q, so I put 2 plus signs. And Q2 was given as 3Q, so I put 3 plus signs. And Q3 was given as 1Q, so I put 1 plus sign. These are all positive. So E1 is the field due to Q1, and so it's an arrow pointing this way, and I called it E1. Clearly, E2 has to be bigger. It's actually going to be 4 times bigger because of the distance, right? It's twice as close, but it's even more charged, so I can't really draw it to scale, but I made E2 the biggest vector. And then E3 is the field. Remember, we're calculating the field at this point. The field's coming from these 3 charges. So this has a field E1. This has a field going in all directions, but at this point it's this way, E2. And Q3 has a field going in all directions, so at the point we're calculating it at, it's in this direction. And it's definitely going to be smaller than that by a factor of 3, right? Because the distance is the same. Okay, so now you should have that figure and try to understand that concept. And now we got to add all these vectors. They're all along the x-axis. They're all I hat. These 2 are positive and this is negative. So write out the equation. E total equals E1 plus E2 plus E3. And then put in the numbers. Should I help you with that? Let's do 1 together. So E1 actually, I'll just take a second. E total equals E1 plus E2 minus E3. These are magnitudes. So if I wanted to be careful, I would put these as vectors, show that they're magnitudes, and the answer is going to be in the direction I hat, the x-axis, right? Okay, so what's the magnitude of E1? It's K, Q, so K, 2Q, over R squared. So the distance from Q1 to the point, that's always the distance you want, is 2D. So that's 2D squared. That's 4D squared. Okay, see if you can do the rest of them. Pause the video and do the other 2, and then come back and check. Okay, did you get this? Now you're going to factor out the K, the big Q, which is a random charge quantity, and the D, which is some random but specified distance. And you'll be left with 3 numbers that you have to add. So see what you get for that. Pause the video and then come back. So there's my answer. It's positive 2.5. You probably have different numbers, but you just do the same thing. Okay, let's take a look at the next one. Okay, we're ready for number 14. Go to Moodle. You'll have different numbers from me, but just go to Moodle and draw a label diagram and label a charge Q and the distances like X and Y. You can put the numbers in if you want, but draw your figure, pause the video, draw the best figure you can showing the point, the two charges, and the two field vectors, and label it. Do it as much as you can. Pause the video before you come back. So you should have a figure that looks like this. You have two equal and opposite charges, whatever the number is, so I'm calling it plus Q and minus Q. I'm thinking of this as Q1, so this is E1. At this point, the field is going away, right? The field is going out like this, so at this point, the field is in that direction. And field lines for a negative charge come in, so the field at this point, due to E2, is toward E2. And because the distances and the charges are the same, these two vectors are going to be the same length, but in different directions. And the distance from the origin to each charge is what we're calling x, and the distance from the origin to the point is what I'm calling y. Those numbers are all given. And so look at the problem for a minute, pause the video, look at the problem, and think about how you're going to add these vectors. Give it some thought before you watch what I do. So just pause the video and think for a minute. Okay, so what you should have thought of is that the y components of the two vectors are going to be equal and opposite. And the x components are going to be equal but in the same direction. And you need to find this angle theta. So to find this x component, it's going to be E1, whatever that magnitude is, times the cosine of theta, whatever that angle is. And what is E1? Try and do this. Don't just listen to me. Write down what E1 is. It's going to be K Q1, which is Q, over that distance. I'm going to call it S squared. You can call it whatever you want. And what is S? It's this distance here, right, from the center of the charge to the point. And so S, actually we have S squared. S would be the square root of x squared plus y squared, right? X squared plus y squared. So that length is the square root, but in the equation we have s squared, so I'm just going to leave it x squared plus y squared. Those are the numbers you're given, right, in the problem. Okay, so that gives us the x component, right, the E1, that's E1, that's what it is. We have to multiply by the cosine of theta, and we'll get this vector. But we also have E2 cosine theta, which is going to be the same length. So what can we do? We can say that the total field is going to be 2 times either of those. Let's just say E1 cosine theta. And the direction is along the x-axis, or I hat. So we need to get theta. Pause the video and see if you can get theta. Okay, there's several ways you could approach this. So this angle, the first thing I would say is that this, since this force goes right through the point like that, and this line is horizontal and this line is horizontal, this angle theta here is the same as this angle theta here. And we could find it, since we have the y and the x, we could take the inverse tan of y over x, and that would give us the angle. and then we could just put it in there. Another way of doing it is to do it in general and say, oh, this angle theta here is the adjacent x over this. So I'm going to do it that way. You can do it the other way. Cosine of theta is going to be x over the square root of this. And E1 is that. So let me see if we can, let's see if you can fill this out. 2E1 cosine theta. See if you can write down what that is, and then come back and compare it to what I get. Okay, here it is. I move things up. 2 times E1 KQ over S squared times the cosine of theta, x over that distance, x squared minus y squared square root, and then if I pull all that together, I get 2kq times x over x squared plus y squared to the 3/2 power. These are all numbers that you've been given. You can just put it in there and get the magnitude, and of course the direction is in the I hat or positive x direction. From the figure we can tell that. Okay, you see the routine, so go to number 15. It's 3 charges and a point arranged in a square. Draw the figure, label the charges, label the distances, show all the vectors, and do the problem as much as you can before you come back to see what I did. Okay, you have this. 3 charges arranged in a square and the point at this corner of the square. So these are the distance from Q1 to the point is S, Q2 to the point is S, and Q3 to the point is S, and Q2 is this distance. So I hope you're getting used to this. If this is S and this is S, this is going to be the square root of 2S. So that distance, I didn't label it as the square root of 2S. And the field due to Q1 goes out, radiates out in all directions. So the field from the charge that goes through this point is along the x-axis, and this field is going out in all directions. So the field from Q3 that passes through this point is going straight up. And since this is a negative charge, the field is going toward the charge. And so the direction of the field at this point points toward the negative charge along the diagonal of the square. That's why this is the square root of 2 times S. So this is going to be weaker than these two. And now we need to add all those vectors. So look at it, think, don't let me think for you. How are you going to add those vectors? And what you should be telling yourself is that along the x-axis you have an x component to E2 that's going to subtract from E1, and you have a y component of E2 which is down and going to subtract from E3. So that will give you the sum in the x direction and the sum in the y direction. And so the total vector at point P, is going to be the x component, which is the magnitude of E1, minus the magnitude of E2, but only the x component, so times the cosine of the angle. You see what it is? It's a square, so it's a cosine of 45 degrees. That gives you the x component. And the y component, so that's in the I hat direction. The y component is what? It's going to be, write it down, don't wait for me, minus the y component of E2. sine of 45 degrees. Of course, that's the same thing. And that's the x component, I hat, plus the y component, j hat. But if we want the magnitude, what do we have to do? The magnitude of EP is the x component squared plus the y component squared square root. And the direction, you can see that these are smaller than these, so these are going to be shortened, but they're going to be equal. So the direction of the final total is going to be along this line, or the 45 degrees from the x-axis. Okay, ready for number 16? No numbers, so that's going to have to be symbolic solution, so we've been practicing that, right? So go to 16, read it, draw the figure, pause the video, draw the figure, and then come back. So here's the basic figure, right? Q1 is on the left and Q2 is on the right, and I'm assuming they're positive charges for now. And you might say, well, is that going to work? Well, we'll see. So if this is a positive charge, the field lines go away from it, and so they'll pass through the point P in that direction. And if this is a positive charge, they'll pass this way. So given this arrangement, remember 1 and 2 aren't equal, so they're not going to cancel. Write down what the total sum of those two vectors are. Write it all out as much as you can. Pause the video and do your best, then come back. So I just wrote it straight up, E1 minus E2, because E1 is positive, when I assume they're positive, right? And so if E2 is a bigger charge, then this vector will be bigger, and the answer will be negative, which it should be. And if Q1 is bigger, then E1 will be bigger, and it'll be positive. Now, supposing they were both negative, so if Q1 were negative, this number would become negative, which it should be, right? If this were a negative charge, it would be in that direction. And if Q2 were negative, then when you put a negative Q in here, it would make this positive, which would make it correct. And similarly, if this were positive and this were negative, they would both be in the positive direction. So for any arrangement, this equation works. So now write out in detail what these two vectors are, and do the algebra as far as you can toward the answer. Okay, see if you got it. E1 is K Q1 over the distance squared, that's D over 2 squared, minus, because we've already figured out that's what we need, K Q2 D over 2 squared. That's one of the choices. But this is kind of clumsy. This squares out to D squared over 4, and then it's a compound fraction, so you should be able to simplify it to this, 4kq1 over d squared minus 4kq2 over d squared. But this is still can be simplified quite a bit by factoring out the 4kd squared, which leaves just q1 minus q2 here. And now you can put any numbers in there that you want and calculate what the field would be here, do at the center between two charges of any sign. Remember, that'll work for any sign, or any magnitude. All right, number 17. Read it, draw the figure, and come back. Okay, check your figure, make sure it's correct. Q1 is on the left, Q2 is on the right. The point is distance x to the right of Q2. I'm starting with two positive charges, so the fields are this way, so they're going to add. If I make both charges negative, the fields will reverse, and so on. So similar to the last one, we can just do it the same way, only the distance from the point to Q2 is now x, and the distance from Q1 to the point, or the point to Q2, is x plus d. So see if you can write that equation out and do the algebra, much like we did in the last one. Okay, pretty straightforward. KQ, the distance squared, plus KQ2, the distance squared. We can factor out the k. The other thing to keep in mind, d plus x and x plus d squared are in fact the same thing, because those are just positive numbers. Okay, you know the routine. Number 18, read the problem. It's similar to 14 but a little bit different, so be careful. Draw the figure, label it, take it as far as you can before you come back and see what I did. Did you get the figure right? Equilateral triangle, distance d, positive charge here, negative charge here, positive E1 vector, E2 vector toward the charge, and now we want to add these two vectors. So you can look at problem 14, you should be able to figure out how to do this. So do as much of it as you can, pause the video, do as much as you can, and then come back. Okay, the first thing to notice is that the y components, by symmetry, because the charges and the distances are equal, are going to cancel. So the y components cancel, so the net field will be in the I hat direction. And E1x and E2x will be identical because these charges have the same magnitude. And so we can say E total is 2 times the x component of E1 or E2. And E1 is simply KQ over the distance d squared, but we want the x component. So the x component, that's EX1, that angle is the same as this theta, and for an equilateral triangle, that's 60 degrees. And so the cosine of 60 equals 1/2. So when you go over here to the cosine of 60, this is going to be 1/2. So 2 times 1/2 is 1. So the answer turns out to be quite simple. But be careful, there is one unsimplified answer, at least one other correct answer other than this. All right, number 19 is the same as 15, only it's all symbolic. So draw the figure and see if you can do the work, and do as much as you can before you look at what I do. There's the figure. There's your square of side S. And so the field due to 1 is that way. The field due to 3 at the point is that way. And the field due to 2 has to, because it's negative, it's got to go that way. Keep in mind, this is not the same distance. So if this is S, this is S. I hope you know this by now. This is the square root of 2 times S, the diagonal of a square. The square root of 2 times S. If you don't believe me, calculate it. So it should be obvious that you got to get the x and y components of this to add the vectors. You can't add them otherwise. So this angle, these angles are going to be 45 degrees, and both of these components are negative. So you have to subtract this from E1, subtract this from E2, And the answer is going to be positive, and it's going to be in this direction. I hope you can see that. So go ahead, try and write the equation and do the algebra as far as you can. Okay, I'm not going to do this all out, but you see, E1, we have to subtract E2x. So the total in the x direction, the I hat component of the answer, is going to be E1 minus this, E2 cosine 45. So E1 is simply KQ over S squared, right? The distance is S. But E2 is KQ over this distance, the square root of 2S. When you square it, you get 2S squared. The cosine of 45, you should know this, it's on your equation sheet, is the square root of 2 over 2. And so when we do all the algebra, we can factor out the KQS squared, and we're left with 1 and the square root of 2 over 4 in the I hat direction. And by symmetry, you should be able to see that the y component is the same. Now to get the magnitude, you have to take this and square it. Although that doesn't show up in the answer. But if you wanted the magnitude, you would take this and square it, and then this again and square it. Or, if you're following me, you just multiply this by the square root of 2 to get the magnitude. And the direction, of course, of the final vector is 45 degrees. It's going to be this way. You can tell by symmetry. So here's number 20. If we go to the center, we have E1 going away from Q1. We have E2. This is a square, so it's along the diagonals. And then we have E3 going toward Q3, and E3 going toward Q4. So it should be clear here that the y components all cancel. And so the answer to this is just 4 times any one of those x components, say E1x. Now to find E1x, you have to know, right, you've got k, q, but you got to get this distance. Well, what is that distance? That distance is half of the diagonal, right? The diagonal is the square root of 2s, so it's half of that. And so when you have square root of 2 over 2 squared, you're going to get 2 over 4, or 1/2 s squared. I'm not going to do it out. The rest is algebra. When you go over here, then Q1 is going to go down along this line, so you got to find that angle. So that's going to be your E1, and your E2 is going to be that way, and the negative charge goes toward, and you can see that those two are going to cancel. And the y components of E2 and the y component of E1 are going to cancel. And so for this one, the total field is going to be 2 times the x component of either one of these. Let's say 2 times E1x. And that's going to be 2 times E1 cosine theta, but this is the angle theta. You see that? And that's not 45 degrees, so you got to find that. And the way you find that is to notice that this is s over 2 and this is s. It's not a common angle. And so this theta here is this theta here, and that's the cosine of that angle that you need. And the E1 is KQ times this distance. And this distance is not the square root of 2 times S. It's less, but it's bigger than S. And so you have to find that by the Pythagorean theorem, or trig. So I'm going to leave that. Okay, I'll give you a little more help. Find this distance and find this angle. Make an effort, and then I'll show you how. Pause the video and make an effort. Okay, call this distance r. I just called it r. So it's going to be s squared plus s over 2 squared. That's s squared over 4, so that's 5/4 s squared. So this distance r is simply the square root of all that, which gives you the square root of 5 over 2 times s. Now what's theta? Actually, let's just find the cosine of theta. All right, getting a little messy, but this angle theta, if we take theta is the inverse tan of the opposite, s over 2, over the adjacent s. So I'm getting theta that way. And so the inverse tan of a half, and it's something like 26 something degrees. And then if you take the cosine of that, you'll get the value. But watch, the cosine of this angle is the adjacent over the hypotenuse. So the cosine of theta is the adjacent s divided by the hypotenuse, this. And so if you take s over root 5 s over 2, the s cancels, and when you invert, you get 2 over the square root of 5. So that's the value of the cosine. All right. Question 21 is about field lines, and if you need to review that or learn it, go to the old video, minute 740, and there's a short discussion there about electric field lines. And the new video has a much longer discussion following a lot of diagrams and explanation about fields starting at minute 25:45. So there you can find the material you need to answer question 21. I think question 22 is fairly straightforward, but let me do a couple of them for you in case you're having problems. So the electric field, what you need to know if you read the directions is that every item, a point, or a charge is separated by a distance d. So the positive charge would put a field in this direction, and it would be kq over d squared. And the negative charge would have a field in the same direction because it goes toward the charge, right? I'm crossing the charge just to make it big enough. And so here you would have two vectors in the positive direction, and you would just add them. And so you would get 2kq over d squared. So the coefficient is 2 times kq over d squared. So that's the answer to A. And then in the case of B, you have a field this way due to the negative charge and a field this way due to the positive charge. So the positive charge is going to be kq over 2d squared. That's positive. You have to subtract from that the field due to the negative charge, which is much bigger because it's closer. Don't get confused that I'm drawing the vector across the charge, right? I probably shouldn't do that. This field goes from the negative toward the charge. I just want to make the arrow big enough. So anyway, due to the negative charge, it's negative because it's in the negative direction, not because the charge is negative, but because of the position of the point relative to the charge. So it's negative k q over d squared. And so if we factor out, this is squared, right? So what you end up with is you end up with the k q over d squared factored out, and you end up with a positive 1/4 and a negative 1. So the answer is a negative 3/4. If you have a point here, like E, where the point is here, and the negative charge is here, and the positive charge is here, now the negative charge is causing a field in the positive direction, and the positive charge is causing a weaker field in the negative direction. So just be careful about that. You're always getting the field at the point. And from what we just did, you can see that the negative charge is going to be a positive 1, and the positive charge is going to be a negative 1/4. So you'd have the same answer, only in this case it would be a plus 3/4. Okay, so 23 is similar to the last one, and there's 6 of them. I'll do E. This is 23E. So when we go to the point, we're going to see, due to the vector on the far left, the negative vector, that's going to be toward the negative charge, and it's going to be quite small, right, because it's far away. Then the second charge, the one in the middle, the field goes away from a positive charge, so at this point the field is positive and quite a bit bigger, but I'm drawing it that way. So this would be E1, E2, and then the charge closest to it, the charge furthest on the right, is going to have the biggest force, and that would be E3, so you got to add all those 3. So since this is D, this is 2D, and this is 3D. Remember, it's the distance from the point to the charge. E3 is going to be KQ over D squared. And E2 is going to be KQ over, right, 2D squared, or 4D squared. 2D whole quantity squared. And the furthest one away, the E1, due to the negative charge, oh, we got to make that negative though. We got to subtract it because it is negative, right? These two vectors are going to add. That's going to subtract, and so this is going to be a negative KQ over 3D squared, or 3D squared, or 9D squared. So negative, when we factor out the K, Q over D squared, I'm getting sloppy, we have a negative 1/9, a positive 1/4, and a positive 1. So that's the coefficient. And if you get the coefficient of each of these, you can then rank them according to the ranking that you're asked to do. So skipping the topographic maps, I'm going to go on to the last question, 25. And this is similar to what you saw in the last assignment on electric force. So if we have a charge spread out in space, how do we use Coulomb's law, which is for point charges? Well, one thing we can do is what we'll do is cut the charge into pieces so that they look like point charges, and then do a summation. But how many pieces do we need? Well, let's do the most simple thing and just ignore the fact that this isn't a point charge and consider it a point charge. So we do this massive oversimplification. We take all of this and just imagine it's a point located at the center of itself. So there it is. I take all this charge Q and I place it in a single point. And then I calculate what is the field if I'm a distance r, right? That's the radius of the circle away. And so it's just simply KQ over r squared. That's what we get for the result. But you can see that that's not going to be correct, because if we divide this instead into 3 pieces, let me do that. Divided into 3 pieces, each piece looks more like a point charge. So this now looks more like a point charge, and it would point this way, and this middle piece would point this way, and this piece would point this way. That's the electric field at this point due to those three pieces. And then we can add those, and we can see that that's going to be smaller because this y component and this y component is going to add. But the amount of charge here now is not q, it's q divided by 3, right? Because we got the whole q divided into 3 parts. And so this middle vector is going to be k 1/3 q over r squared. And this piece is also k 1/3 q, k 1/3 q, but the only part that adds is the x component. And the x component, this ends up being 60 degrees, and the x component is 1/2. So we have 1/3 here, we have 1/2 of 1/3, plus for the other one, another 1/2 of 1/3. I hope you're following this. So the first piece is 1/3 kq over r squared. The next piece is only half of that. And the last piece, right, these two pieces to the side, is half of it again. So it ends up being 2/3. 1/3 plus a half of 1/3 plus a half of 1/3 ends up equaling 2/3. So we get a smaller value, which makes sense. Okay, if we want to go further and get a better result, we divide this into 5 pieces or 9 pieces or whatever number of pieces. But if I divide it into 9 pieces, now they're really starting to look like point charges, but each piece only has q over 9. And then for each, you're going to have 9 vectors, right, at all these different angles. So you do have to find the angles, and you have to get the cosine of each one, and it comes in pairs. It's not that bad, actually, when you go to do it. But the ultimate best solution is to go to this point and divide this into an infinite number of small pieces and get the electric field by doing the integral over the entire half circle of k times each little piece dq over r squared. Why? Because each piece is a distance r. That makes the problem easier. It's actually a fairly easy problem as far as calculus problems go, but I'm not going to take the time to do it here. Okay, I'm going to pause and give you a table of contents to refer to in case you want to just find something in this video and not look at the whole thing. Okay, there it is, your table of contents, all the problems I did and the times at which I started doing them. So if you're just interested in 17, go to minute 1951 and you'll find it there, and so on for any of the other ones.